Hello everyone, welcome to COMP359, Design and Analysis of Algorithms at University of Fraser Valley. In this video, we are going to continue our discussion about divide and conquer approach and solve another problem using divide and conquer approach. This problem is called finding median. So the problem is very simple. Simple to explain. You have n distinct numbers. You are looking for the median among these n numbers. So I think the problem is easy to understand. How we can solve this? A naive algorithm that first came to mind is that, okay, we can sort the numbers and finding the median is very easy. So the middle item is going to be the median among these n numbers, right? What is going to be the cost? We know that we can solve, the best sorting algorithms that we have can work in n log n. So that's it. Sort the array, find the middle item that's going to be the median among the n numbers. But of course, we are not interested in these naive algorithms, right? So we are going to try to solve the problem using divide and conquer approach and find an algorithm that works faster than n log n. So if you think about it, actually solving this problem directly as it is using the divide and conquer is not going to be really easy, or at least it's not very actually simple to find a way that you change the finding median and created some subproblems that actually come back to itself. So what I mean by that is that, so assume that you have an array, you are looking for the median item, you are looking for an item that actually falls in between all the numbers. It's going to actually fall in the middle of all the numbers when you are ranking them, right? So if you are going to create some subproblems, finding the median in, for example, half of the problem is not going to help you to find the problem, finding the median among the full n numbers, right? So this problem is not going to be easily reduced to itself. It's not easy to find a recursive relation for such a problem, which is, directly asking for the middle item among n items. So finding the middle item among n divided by 2 of the items is not going to really help you. So what I'm going to do is to change the problem, to change the main statement of the problem and solve another problem which is more general than finding the median. And if we can actually solve this problem, then we can also actually solve the finding the median problem. Okay, what is this more general problem? It is saying that, assume I have n distinct numbers. I am looking for the kth smallest item. So the n number is given as an argument to this problem, and the value of k, which is going to be the rank that I'm looking for, the value of the k is also an argument to this problem. So k can be anything. Kth smallest number. It can be actually the smallest item, the fourth smallest item, the 10th smallest item, right? So this is more general than finding the median. And if you can solve this problem, instead of, you can actually just say that, if I have, 25 items, let me actually, I can solve the kth smallest problem. So solve the 13th smallest problem in such an array of size 25. So that's going to be the median, right? So you can see that this is more general than the median, and if we can solve this, we can actually find the median as well, right? So I'm going to change the problem to this more general form problem. And the nice thing about this problem, although this is more general, but there is something actually very nice about this problem, that this problem is reducible to itself. So I can find some recursive relation for such a problem. What is the idea? The idea is very similar to the partitioning idea, the idea for finding the recursive relation here is very similar to the partitioning idea in the quicksort algorithm. So let's just remind what we do in the quicksort. In the quicksort, there is a partitioning step. Remember, we actually in one step before calling the recursive quicksort recursively, we had partitioning step. What we did in the partitioning step of quicksort was that you had an array, right, and you choose a value as a pivot. So just here assume that we randomly choose a value as a pivot. You pick a value among n items in the array, and then you partition the array around that item. So for example, if randomly you choose, for example, this item and pick it and say that, okay, this is going to be the pivot. Okay, what we do is we call the partitioning method and partitioning method partition all the values around the pivot, put the pivot value at its correct rank. Let's just call that rank R. So it's just like that value will actually end up to its correct rank among n items. And also all the items on the left of the pivot will be smaller than the pivot. All the items on the right of the pivot will be greater than the pivot. So these items are going to be greater than the pivot. These are going to be smaller than the pivot, right? So we also knew one more thing about the partitioning, that the partitioning could be done in linear time. Okay, so let's just actually put all this information and see that how we can use this approach of partitioning to create some smaller subproblems for the original problem of finding the kth smallest item. So I am going to solve the kth smallest item. I'm going to find a recursive approach for that. What I'm going to do is choose a pivot value, partition the items around that pivot value, something like this. That assume that this is your array at first. You choose, for example, the value of 4 randomly. For now, just assume that we randomly choose this pivot. We partitioned around the pivot value. 4 will be placed at its correct rank. Let's just call it, this will be actually the rank R. All the values in the array which are smaller than the pivot 4 will be actually placed before the value of the 4, and all the values greater than 4 will be placed after the value of the 4. Okay, so now assume that we are still looking for the kth smallest item. Okay, kth smallest item. I don't know what is the value of k. There are going to be 3 possibilities for k, right? Either the value of k, this rank k that I'm looking for, is equal to r, or k is greater than r, or k is smaller than r, right? If the rank k is equal to r, what would happen? The rank r is the rank of that pivot value that we chose randomly. Okay, pivot. So if we we are looking for the, for example here, the fourth smallest item, and the rank here happened to be fourth. It's just, you know, by chance that the rank and the actual pivot value are the same. Probably I should actually pay more attention and choose another item here, for example 5, let's say. So forget about that. Let's just say that if the value of k is equal to the rank of the pivot, we are lucky, we found it, so we are done. No more actuating. So you can actually just return the value of 4, for example, here, and say that, okay, this is going to be the fourth smallest item. But what if the value of k, the rank that we are looking for, is greater than r? So that actual value that we are looking for will be in this part of the array, right? On the right side of the array. And we can call the same problem, we can call the problem of finding the kth smallest item, but just actually changing the value of k. Because if I'm looking for the value of k greater than r, that value is going to be, for example, it's going to be the kth smallest item. And that will be happen in this side of the array. And so far, art value of the items will be actually removed from the problem, right? So the problem will be of size n minus r, and you are looking for the k minus art rank, right? Because it's just like you are the actual rank k in this problem will be the problem of finding k minus r rank, because already this part of the array will be removed. How many of the items? R number of items. So you have to reduce r from k. But what if the value of k is smaller than r? If the value of k is smaller than r, so you are looking for the kth smallest item on this side of the array. How many items you have in this side? R minus 1 number of items, and you are still looking for the kth smallest item. The value of k is smaller than r, the rank r. So as you can see, there is going to be actually these 3 cases. The value of r is equal to k, so we are done. You can actually return the item that you found, the pivot value that you found. If the rank of the pivot is greater than k, you are still looking for the kth smallest item on this side of the left side of the array. If the value of k is greater than r, you are looking for the k minus art item on the right side of the array. That part of the array that after the pivot. Okay. So these 2 subproblems are exactly the same subproblem, just changing the argument. The size of the problem will be changed, and also the that kth argument might change. So here you will actually still look for the kth item. Here you need to actually change it to the k minus art item. This is an argument to the problem, so it can be changed. This is not changing the size of the problem. The size of the problem will be the size of S1 and the size of the S2. For the S1, the size will be r minus 1. For the S2, the size will be n minus r. Okay, but you solve only one of these subproblems. Either this one it needs to be solved, or this one, not both of them. Okay, so now I can actually write down the recurrence relation for the time function of this algorithm that I just actually discussed, that you use the partitioning, choose a pivot value. Based on that, you actually would have one of these 3 cases. So now we can actually write down the recurrence relation for the time function of this algorithm. So the problem here will be, let me actually use the correct pen. the problem here will be of size r minus 1, the problem here will be of size n minus r. Okay, but they are exactly the same subproblem. Either I need to solve this one or this one, but not both of them. So when I'm writing the time function, this is going to be either solving t of n minus r or solving t of r minus 1. Okay, and there is going to be some cost of the partitioning that I'm going to write it as O of n. But which one I should write? This one or this one? If you have, the cases like this, that you don't know which one you are going to solve, you need to always go with the largest size, because this is telling you the worst case, right? So t of n will be the maximum of these two, t of n minus r and the t of r minus 1 plus O of n. But which of these are going to be actually maximum? This is in fact based on the size of them. If n minus r is bigger, then t of n minus r is going to be actually bigger. If the other ways, then this one is going to be bigger. Okay, so one thing that I can actually, one way to write it down is using this way. That's saying that t of n is going to be t of n minus r plus O of n if the value of r is less than n divided by 2. And I think it's actually clear here that if r is less than n divided by 2, you can actually just conclude that n minus r is going to be bigger than r, right? This problem size is going to be bigger, so that's why I wrote it as t of n minus r if the value of r is less than n divided by 2. If the value of r is greater than n divided by 2, then the other subproblem here, this subproblem is going to be actually bigger. So I just simplify it and wrote it as, for example, t of r plus O of n or t of n minus r plus O of n, depending on the value of r, if it is greater than n divided by 2, or it is less than n divided by 2, or it is greater than n divided by 2. So now you can actually see that everything would be depending on choosing the pivot value. If the pivot value that I choose is something like, for example, r equal to n divided by 2, the relation, both of these two cases, this one and this one, both of them are going to be of the same size. And what would happen to the time complexity? The time complexity in that case will be t of n divided by 2 plus O of n, right? So it's actually exactly talking about this fact that, okay, if I choose the pivot to be something in the middle or almost in the middle, it is just like always you are making the problem of the size half. So either this half or this half will be removed, but always half of the size will be removed. So always the value, actually the recurrence relation that you are going to solve is going to be this one, based on the cost is going to be this relation. What if the pivot value that I choose is something either very small or very big? So in that case, for example, if the rank, the pivot is here, then the problem that you need to solve is going to be as big as this part. So that's going to be actually a problem of size n minus 1. Or if you choose a pivot which is actually very big, so the problem that remains to solve is going to be again of size n minus 1, right? These two cases are going to actually cause a time function with this formula, t of n minus 1 plus O of n, right? So I can actually go as good as this or as bad as this. if you solve this reoccurrence relations, in this case, T of n will be O of n. You can simply just solve it using the recursive theory, or even the master theorem will tell you that this is going to be O of n. This one is not solvable using master theorem, but using the substitution, you can simply check that this is going to be O of n square. Okay, so you can, based on the value of the pivot, if the pivot is some extreme, something very close to the beginning of the array or very close to the end of the array, this is going to actually be the recursive relation, and the time complexity will go n square, which is even worse than the naive algorithm that we discussed, which was n log n sorting. Or if you choose a pivot value which is in the middle, this is going to give you a good reoccurrence relation like this, and the time complexity is going to be linear. So our problem here became the problem of finding a good pivot value, some pivot value which is close to the middle point. But can we do that? Because you remember the original problem that we were solving was finding the median values. So if here I'm going to find a pivot value which is the median, this is really the original problem. It is not really easy to solve that one. So it's not going to be easy to find a pivot value that is the median of the items, or close to actually, or something that actually gives you the n divided by 2 as the pivot, as the rank of the pivot. But there is there is a claim here, and that is the fact that if I don't really need to find a pivot value that gives me exactly the rank n divided by 2. Even if I find a pivot value that I can prove that the pivot value is, for example, something like between n divided by 10 and 5n divided by 10. So it's just like I am claiming that I can find a pivot value that is going to end up like in this area where this part is n-tenth and this part again is of size n-tenth. So in that way you are actually saying that R, the value of the rank of the pivot, is between n-tenth and 9n-tenth. Okay, so you're actually just saying that the pivot value is in this interval of all the numbers. Okay, this is not exactly n divided by 2. This is not very close to n divided by 2, but still it gives me, a very important thing about the time complexity. If I can actually claim that I can find a pivot value like this, a pivot value with a rank like this, I can show that the time complexity of the algorithm will be this one, right? Because you can actually just say that R n minus R is going to be n minus R is going to be 9, it's going to be actually less than 9n-tenth, and the value of R is also going to be actually less than 9n-tenth, right? So the maximum of the subproblems is exactly 9n-tenth. So the time complexity will actually be solved using this reoccurrence relation. Okay, so if you solve this reoccurrence relation, you can see that exactly because of this rank 9 over 10, the time complexity of this is going to be O of n. You can solve it using either the master theorem, or you can draw the recursive tree and see that the time complexity of such a relation, the solution for such a relation is going to be linear. Okay, so this is very good. If I can find such a pivot value, then still the full algorithm for finding the kth smallest subproblem will be linear. Okay, now our problem is to find kind of such a pivot value that I can prove it. This is going to be between, for example, n-tenth and 9n-tenth or something similar. It doesn't actually need to be exactly this. For example, if you can find something like n-third and 2n-third, this is going to give you exactly the same answer for the time complexity. Or for example, n-fifth and 4n-fifth. All of these are going to actually have the same effect in the solving the time complexity. So now I'm going to actually tell you that yes, there is an algorithm that we can apply it, and this algorithm I can actually just prove that it always gives you a pivot value that will end up in this interval, 3n divided by 10 and 7n divided by 10. This is still giving me exactly the good properties of the previous relation that I proved. This is going to be, for example, 10n divided by 10, 3n divided by 10, and this is another 3n divided by 10. And the value of the r will actually, the value of the pivot will actually will fall in this interval somewhere here among all the nth number. Okay, so what is this algorithm? I'm going to explain the algorithm here for you first, and then we actually get back to the analyzing the time complexity of the original problem. So this problem of pivoting, this algorithm for finding the pivot is telling you to divide all n items that you have into groups of 5. Okay, so in each group you are going to have, let me use a different, okay. In each group you are going to have 5 items. Okay, so something like this. And if your n is not divisible by 5, it doesn't matter. The last group is, we can actually have less than 5 items. Okay, here I'm just assuming that all of the groups are 5. Then find the median in each group. Okay, so let's just assume that we found the median in each group, and I'm going to actually put it in between. Finding the median in all of these groups of 5 is going to take, each of them is going to take constant, right? It's going to actually be O of 1, because if you have just 5 items, finding the median is going to be constant for 5 items. But of course this is correct that if you have n divided by 5 groups, divided by 5 groups, then in total this is going to be actually costing linear. That grouping part is also going to cost linear, so let's just forget about the time for now. So the first step, divide all n items to groups of 5, find the median for each group, and the last step is that telling you to find the median among all the medians. So among these this filled dots that I have here, find the median among all these. So let's just assume that that group that has the median of the median is this group. I just put it here. So Something that I know about, I'm going to first prove this claim, then get back to this cost, because I'm sure that now you are asking what is going to be the cost of this one. So before actually getting back to that cost, let me tell you something about this. The claim that this median that I found, just this median, this is, I'm claiming that the rank of this one is going to be between 3n divided by 10 and 7n divided by 10. Okay, so if this is, let's just actually killing this part. If this median here, if this is the median of the median, I can actually say something about these groups. Let's just say that this is like I haven't actually really sorted these items, but I can say something about them. That, for example, these two that I have here are going to be smaller than this median, right? And these two are going to be smaller than this median. These and all of these for these two are going to be both of them smaller than this median. These are going to be smaller than this, and these are going to be smaller than the median. These are the median of each of these groups, right? And these two are going to be greater, these two are going to be greater than the median of its own, and these two are going to be greater than the median of this part, this one. Okay? One thing more that I know is that this is going to be greater than all these medians that I have here, and smaller than all these medians that I have here, all of these groups here, and this one for all of these groups here. Okay, so this median is going to be greater than this one, greater than all these medians, and all of these medians, each one are going to be greater than their own half of inside that group. Okay, so what I know about this median of the median that I have is that this is going to be greater than all the items here, right? You agree, right? And this is going to be also similarly, I can say that this is going to be smaller than all the items here. So how many items I have here? I can claim that how many groups I have? I have n divided by 5 group. So if this is the group that contains the median, right? So this part is going to be half of those n divided by 5 groups. So all of the items that all of the actually groups that I have on this side are going to be n divided by 5 divided by 2. So this is going to be n divided by 10 groups. Similarly, the number of groups here is going to be half of the groups, right? So this is going to be n divided by 10 as well. N divided by 10 groups. In each of these groups, 3 items, 1, 2, 3. 3 items, I know that they are going to be smaller than the median of the median. So 3 multiplied by n divided by 10 items are going to be in this box. They are going to be in this box. Let's just actually use a different color. How many items are going to be there? They are going to be greater than 3n divided by 10 items. How many are here? Exactly the same amount I can actually just assume, because this is going to be, and it is going to be again 3n divided by 10 groups for this side. And I know that the median of the median is going to be greater than all these items, smaller than all these items. So that is going to be if you find the rank of this one, the rank of this one is going to be greater than 3n divided by 10 and smaller than 7n divided by 10, right? So this part is telling you that this is all the n items. How many items here? 3n divided by 10 item here, 3n divided by 10 item here. So this is going to be between 7, the rank is going to be between 7n divided by 10 and 3n divided by 10. So this is the proof for the rank. Now our question is that what is going to be the cost of finding the median of the medians? You have n divided by 5 items. You wanted to find the median among these. And you remember, this is the original problem that I have. The problem of finding the kth item, in fact, actually, you can think of it in this way, that this is going to be recursively called in this part as well. And the cost of that is going to be t of n divided by 5. Okay, so now let's just get all these times that I have, take it back into the original actually problem that we had. Okay, so the cost here, this is going to be the cost of the pivoting. Okay, this is the cost of finding the median of the medians. Linear here, linear here, so I'm actually showing it as C2n. So this P of n is going to be the cost of the pivoting. T of n is the cost of the original problem finding the kth number. Okay, so now I'm going to take this one, put it inside the this is the relation that I have for the, this is the relation, remember this was the original relation that we find for finding the kth item, the kth smallest item in the in n items, right? And based on the fact that the value of the rank of the R, we can actually just say that, okay, that R, the pivot that we found, was supposed to be between 3n divided by 10 and 7n divided by 10, right? And based on this, I can actually say that this part is going to be t of 7n divided by 10, right? And instead of that O of n, I wrote C1n. So this is the original actually cost that we had, and now we have to actually add the cost of the pivoting as well, which is going to be that P of n. P of n from this formula is going to be something like this. Remember, this is that T of n divided by 5 is coming from that P of n. And some other linear cost is also going to be added, which is, I'm adding it here, and I am replacing this C1 plus C2 with C of n. This is going to be some linear cost. So now our problem is to solve this full relation. That I can actually tell you that this is going to be linear, but if you don't, if you really need me to show it to you, this is going to be something like this. Let me actually draw the tree. So this is the relation that I have. T of n is equal to T of 7n divided by 10 plus T of n divided by 5 plus n. Instead of Cn, I wrote n, so just actually to simplify it, 4/3. So T of n is going to be, these are those recursive functions that I have, right? 7n divided by 10, n divided by 5, (49) n divided by 100, (35) n divided by 100, (35) n divided by 100, n divided by actually 25, right? And you can actually just grow the tree. There's something about this tree. Of course, the tree is going to reach to the leaf node here faster because you are no, this on this part is going to actually reach faster on this side. So here it is going to actually reach to the leaf node faster than this side. Okay, so the tree is going to be uneven. So what we can do is to find the cost of the lower bound and some cost for the upper bound. We actually solved something similar to this in the previous video. And if the lower bound and the upper bound are the same, we can actually say that the theta is going to be the same as this one's. Let's see that if we can actually find the same cost. So the cost of each of these boxes, here I have linear, right, because of this. Here I have 7n divided by 10. Here I am going to have n divided by 5. Here I am going to have 49n divided by 100. Here I'm going to have 35n divided by 100, 35n divided by 100. And here, let's just actually, instead of, that's going to be n divided by 25, right? But I can, instead of this one, I can write it as 4n divided by 100 as well, okay? And then what I can do is that just get the summation for each of these levels. For the first level, this is going to be n. For the second level, this is going to be 9n divided by 10. And for the third level, if you add up all these 49, 35, 35, and also it's this 4n divided by 100, you will actually end up to 81n divided by 100. Okay, so there is something about these costs of the levels. What I can see here is that I can actually take n out, and it's just like there is a ratio here. You can actually see that this is going to be the summation of n multiplied by 9 divided by 10 to the power of I equal to 0 to what? Log of n, where for this one the log of n will be in the base of 5. For this one the log of n will be in the base of log of n in the base of 10 divided by 7. Okay, so you can see that it doesn't matter the value of actually that log of n. This ratio is smaller than 1 from the that formula that we discussed in the master theorem. This summation is going to be constant. So what would remain for the lower bound and for the upper bound, both of them is going to be actually linear. So the lower bound is going to be linear, the upper bound is also going to be linear, so the total time complexity, the exact actually growth ratio, will also be linear. So I can actually prove that this recurrence relation will be linear. I know that the algorithm is kind of became very complicated, so I would recommend you to go back and read the full section of 9.3 in your textbook, which explains this algorithm of medians and how to solve it. It's actually just explained everything in your textbook. After that, come back and read the slides here again. I'm sure that you will find it way more understandable. And I also have a very interesting actually exercise for you here, that in the algorithm of finding the pivot, the algorithm for finding the pivot, let's just actually assume that, remember, we divided the items into groups of 5. And we found this final time complexity, the reoccurrence relation for the time, which was actually end up to the linear. So instead of dividing the items into groups of 5, try that pivoting algorithm. Try it with dividing all the items into groups of 3, and see that using these groups of 3, what you will get as the reoccurrence relation, and so what will be the final time complexity. And also try it with 7 elements. See that what you are going to get as the again the reoccurrence relation in this case, and what will be the final answer. So you will actually see a very interesting result, which kind of justify why the group of 5 is the best answer. Not exactly the best, but it's kind of actually the simplest, while still it is going to give you the linear time. Okay, try it with groups of 3 and also groups of 7 as your exercise. If you had question, we can talk about it during the office hours or in classroom. I have one more exercise here for you. This is from your textbook. I will actually post the solution for this one as well. And there is one more problem solved in the slide as well, closest pair. This one is also available in your textbook. I have referred to the reading for this one as well, but I'm going to actually leave it here for you to read it. I have written the full explanation here in the slides, and you can actually read it in your textbook as well. So this is just another problem that can be solved using the divide and conquer approach. So for this week, the main actually purpose of this week was more solving more interesting problem using the divide and conquer approach, and showing you different ways of applying this approach. The reading will be continuing actually doing the exercises for chapter 4, section 33.4 for the closest pair, 9.3 for the finding the median. You can also find some related sections in the Klingberg-Tardos textbook if you have it. That's going to be section 5.3 and 5.4.